So the fairly vague instructions that I was given were to cover questions of dark matter models, and that's pretty open in terms of what that can mean. So I've decided to take that in a few different directions in different lectures. So obviously I'll be lecturing about what kinds of models are people talking about today, what are the differences between the models, what are the motivations for models. But what I want to start off the discussion with today is a sort of a general background, which is that if you are somebody who is approaching dark matter model building for the first time, what is it that you are trying to keep in mind? What are sort of the basic things you try to take into account, and how do you think about these models? So I know that you heard quite a bit about lambda CDM last week, and that's great because I can then take some of that as a given. But I want to reintroduce some of it because the way that particle physicists deal with cosmology obviously is different from how cosmologists deal with cosmology. So I want to start off with a cheat sheet for cosmology. This is going to fall off. Is there something we can do to make it not fall off? I mean, I don't. Huh? It gets bigger.
You're supposed to put these as ear hooks.
I did.
And then this is behind your back.
Oh, this goes. Okay. Maybe it's my glasses. So, all right, we'll try. We'll keep trying. So, if you can't, no, we're gonna do this all day. If you can't read my handwriting, then let me know because my handwriting is not great. I don't take offense if you need me to clarify something. So. Thoughts? Do you have another microphone? Just this microphone? Yeah. Okay. It just keeps coming off, is all. And I'm trying to, keep it on. All right, I'll just keep talking and it will fall off. So in an expanding universe, we all learned last week that you can describe this by a scale factor, A of t, right? So A of t, as you learned last week, is a component of the metric. So if you have a dx3 squared, if you have a homogeneous isotropic expanding universe, then there's a simple metric that you can write down, which is described like this, and all the dynamics of that expansion, at least in a homogeneous sense, are dictated by this A of t. And we describe the expansion by the Hubble parameter, 1 over a dA dt. And already here, I just want to take a moment because, yes, you all know the Hubble parameter, but there are already differences between how cosmologists think and how particle physicists think because there are different ways that you can think about this Hubble parameter. So first, you can think of this, of course, as a distance velocity relationship. This is the good old-fashioned Hubble's law. And that's the way that most of us learn what the Hubble constant or the Hubble parameter is to begin with. But it is also a time scale for which the universe changes by order 1. Now this is handy because this is going to be an important question for us in asking things about whether the universe is in equilibrium or not in equilibrium. If processes happen on time scales which are much, much shorter than this time scale, then you can effectively treat the universe as being a steady, unchanging state. If you have processes that occur on a time scale which is longer than this, then you have to take into account the expansion of the universe. And lastly, this is a distance scale. Which is, of course, the horizon size. Which is more or less the size of the universe at any point in its history. And as I said, I just want to go through this because I was told I can flip this. Oh. I go like this. This is I will erase. And the reason that I'm going through all this is because I want to make sure that we are all on the same page in dealing with these sorts of early universe calculations and have reasonable facility in talking about these quantities and dealing with these concepts. So this is, of course, something which is very important if you want to think about the universe cosmologically. But these are the critical ways that we should be thinking about the Hubble parameter as a particle physicist. Now, in a flat universe, we also learned this simple relationship that the Hubble parameter squared is proportional to the energy density rho, where rho is the energy density in matter plus the energy density in radiation plus whatever you want, any form of energy density. And Newton's constant is just set by the Planck mass of approximately 10 to the 19 GeV to the minus 2. So for a given energy density, we use the relationship, which is just which is usable when it's usable and not when it's not. Properly, this should be a derivative relationship, where there's a relationship between the pressure of a fluid and the energy density, and an equation of state parameter W. We can put then different categorizations on the different parameters of equation of state that we see. For a cosmological constant, you have an equation of state minus 1, and the energy density dilutes as a to the minus 3w plus 1. So a cosmological constant has a pressure which is equal and opposite to its energy density. And you plug in minus 1 up here, and you get that rho is just equal to a constant, as it should be. For dark matter, it's pressureless. That's a critical part of what we mean when we talk about cold dark matter. So it dilutes like a to the minus 3. And radiation has an equation of state, a pressure of 1/3. And so its energy density dilutes like a to the minus 4. And these things are all very, very simple in how to understand this. Obviously, energy density that's associated with space does not dilute as the universe expands. If I have dark matter, then I'm saying that I've got a box full of stuff, and as that box expands, the amount of stuff in there stays the same. So the only decrease in the energy density is just the size of the box itself. For radiation, you've got photons, and you have a number of photons in the box. The box is getting bigger, so they're diluting like a to the minus 3 as well. But each individual photon is also stretching out its wavelength, so the energy density of every individual photon is dropping like 1 over a also. So this is no dilution. This is just dilution. And this is dilution plus redshift. And all this stuff is, I know, things that you saw last week And that's why I can go relatively quickly through this. But I'm happy to go back and discuss any of this stuff. I hope nobody will feel that they are unable to interrupt, ask questions. That's what we're all here for, right? So please do. So, so this last piece here, that the energy density of radiation dilutes like a to the minus 4, is critical because the temperature of this photon bath then, or of any radiation, absent entropy production, is decreasing like 1 over A, right? So as the universe expands, the temperature is dropping. And this is very useful to us because A is in some sense a time parameter, right? A is telling us about some monotonic evolution of the universe as the universe expands. And so if the temperature is dropping off monotonically with that expansion, then that means that we can use this temperature as its own time parameter. And properly, T inverse is the time parameter that we want to use. It's nice, it monotonically drops, so as you move forward in time, it's getting lower, so the inverse temperature is getting larger, so it has all the properties that you would like in a time parameter, except for that it has a different physical meaning than time, and has a much more useful physical meaning. So the last thing then that we need to say when we're talking about our early universe properties is the energy density that we have of the different fluids. This you can look up in any of your favorite textbooks on early universe cosmology. That the energy density in a relativistic fluid, which we just generically call radiation, is stuff times T to the 4th. G here counts the number of degrees of freedom, so that can be spin degrees of freedom, that can be internal symmetry degrees of freedom, whatever you want is counted by G. But this parameterization is obvious because if you have a relativistic fluid, then there are no other dimensionful parameters that are relevant in your theory. The only dimensionful parameter you have is T. So if you want to write down an energy density which has dimension energy to the 4th, then the only quantity you can write down is numbers times T to the 4th. Okay? And so very often when we're doing estimates about the properties of the evolution of dark matter in the early universe, we'll simply take this to be T to the 4th. And non-relativistic matter has an energy density which is just the number density of the particle times the mass of the particle. And the equilibrium number density of a particle is, now we have the mass scale in the theory, so the appropriate dimensionful factor is m times t to the 3/2. So instead of t cubed for the number density, it's mt to the 3/2. But then if you're in equilibrium and you're non-relativistic, there's this critical e to the minus m over t factor, which tells you that when the universe gets cold below the mass of the particle in question, that the number density is going to be exponentially suppressed. And you all remember this from your early lectures in statistical mechanics. Intellectually or intuitively, this is just the fact that in the early universe, if you simply have two massive particles that can annihilate and stay in equilibrium with the thermal bath, then they will always be able to convert energetically into the thermal bath. But to find two, say, photons that can produce the particle chi in question, you'll have to go way out on the Boltzmann distribution to find two such photons. So the process of producing this particle is exponentially suppressed, whereas this particle is perfectly happy to annihilate itself away whenever it finds another one of itself. Good. So when I said this is a cheat sheet for cosmology, I was being serious. This is a lightning review. but just to make sure that we all have it written down somewhere. So the Hubble parameter, if you have a radiation-dominated universe, gives you a Hubble parameter which is approximately t squared over m Planck in the early universe. Now, there's this G star factor out here, which is counting the total number of degrees of freedom which are in thermal equilibrium, relativistic degrees of freedom in thermal equilibrium. But in the standard model, that number never gets much larger than 100. And even in theories where the, like supersymmetry, where you dramatically increase the number of degrees of freedom, this G to the 1/2 is not ever going to be much more than an order of magnitude or 2. And when you're talking about the types of calculations that one does in terms of particle cosmology, very, very, very few of them do you ever have to do at a very precise degree. Because the universe is going over tremendous orders of magnitude, right? You're going from temperatures of 10 to the 19 GeV possibly down to current temperatures of 10 to the -4 eV. You're talking about number densities which can be exponentially suppressed by tremendous factors. And so typically what one needs to calculate in the early universe context of various models is just to see whether two things are approximately equal. And if they are approximately equal, then you do a careful calculation. But more often than not, one will be much, much larger than the other, or vice versa. And so these sorts of estimates are critical in developing your intuition as to how these sorts of models behave in the early universe. So you don't need to always be sitting down with your numerical code and working out what the Hubble evolution precisely is. Very often you can do a lot just by taking this t squared over m Planck times some order 10 number. So the history of the universe, then, and this I know you saw, looks like this. So here is log of the energy density of some species in question, and here is log of inverse temperature. So at early times, you have a radiation component which is dominant, and this component is dropping off like t to the 4th. In contrast, you have some matter density, which is going to ultimately be the dark matter, which is dropping off like t cubed. And remember, this is dropping off like t cubed because t itself goes like 1 over a, and the number density of a dark matter particle of relativistic matter, non-relativistic matter, drops off like a to the -3. So t cubed is that a to the -3 factor. And then you have, of course, the cosmological constant, or dark energy, depending on whether you're in lambda CDM or in an extension of it. And so you have these different eras of the universe, right? So if you go far enough back, the universe is radiation dominated. The energy density of the universe is approximately t to the 4th. And the Hubble constant in that time period goes like t squared. Then, at a temperature of right around an eV, so here, this, let me just write this. This is a temperature of around an eV. So z of redshift of about 3300. You have matter radiation equality. And shortly after that, you have recombination. The fact that you have that period of time is very, very important. At about z of 1200, or t of about 0.3 eV. And then we live in this matter-dominated era all the way out until the cosmological constant takes over, or dark energy takes over, and there we switch over, and the Hubble constant becomes the Hubble parameter becomes a constant, or is becoming a constant. So now we can actually start getting into some of the details of dark matter and how the dark matter works. Because the point of all this is not just to make you write down furiously a bunch of formulae about how the early universe behaves, but to remind us of what the parameters are that we're working within. And one of the parameters we're working within is that the universe begins with adiabatic perturbations. So we have perturbations in all the fluids. And those perturbations, in particular in dark matter, are critical to our knowledge that dark matter is there. And these perturbations for dark matter grow logarithmically with scale factor during radiation domination. And these perturbations grow linearly with scale factor during matter domination. And then the growth falls off as you move into dark energy. And that's going to be critical because that means that if you have a fluid that's made out of just dark matter with no pressure, then even though it's radiation dominated in this time period, those perturbations, those initial delta rhos over rho that were given by inflation or whatever, have been growing logarithmically all this time. Then you get to matter radiation equality. You shift over to being matter dominated. They start growing very rapidly, like A, and they ultimately then give us the structures that we observe. Questions about any of this? Yeah?
Do you mean that radiation domination is considered dark matter?
No. So what I mean is that that's a very, very good question. So what I mean is that let's go back in time, back here. I've got some component of non-relativistic dark matter back then, and I've got perturbations in it. Those perturbations are trying to grow, right? So you've got some inhomogeneity. So there's some more stuff here than there is elsewhere. It's trying to pull stuff in. But in a radiation-dominated universe, so much of your expansion is dictated by the radiation, and that radiation is not clustering. And so it's very hard for that dark matter perturbation to grow during radiation domination. So I'm thinking of cold dark matter, but during radiation domination. And so its perturbations are growing slowly, but growing nonetheless during radiation domination. Once you get into matter domination, then the dark matter is dictating essentially everything, the dark matter and the baryonic matter together. And then those perturbations then can start growing very, very rapidly, because if I've got more stuff here, then that's dictating, that's an overdensity in everything, and that entire amount of stuff is going to start clustering and amplifying that perturbation. That's a very, very good question, because that's actually ambiguous from how I wrote it. So this is going to form the backdrop of the things that I'm going to say for the rest of the lecture. I'm going to say one last thing then, on the spirit of cheat sheets. And that is a cheat sheet for equilibrium. So one of the very important questions that we're going to be asking again and again and again is whether a given process is in equilibrium. And I know that this is a question that came up in the context of baryogenesis, Big Bang nucleosynthesis already. And so the critical comparison that we're always making is whether a given rate of a given process is bigger or less than the Hubble parameter, right? And the reason for this is simple. Is that if I have a rate which is lower than the Hubble parameter, then that means that if I wait for that process to occur once, by the time I've waited for it to occur once, the universe has already changed its properties by order 1. And in particular, what you usually think about is I've got some number density of particles that are trying to annihilate on themselves. That's the sort of standard thing that we think about. And it's flying around. It's flying through some background of particles. And as the universe is expanding, if in one Hubble time it hasn't encountered itself, another particle like itself, then the number density is dropped off by a factor of 1 over a cubed. And that means the number density has gone down significantly, and my chances of finding another particle in the next Hubble time are even worse. So this is the critical question for equilibrium, because if you wait one Hubble time and your process hasn't happened, then in general, although not always, I'll discuss the exceptions, not always, but in general that means that if you didn't have it happen in the last Hubble time, then you're not going to have it happen in the next Hubble time, and you should just kind of give up. Let's do an example of this, an example that I'm sure you've all done, but it's very healthy because it shows you the kind of estimates that you need to be doing when you're doing particle dark matter calculations. So it's the question of neutrino-neutrino freeze-out. So neutrinos annihilate into E plus E minus in the early universe. They're relativistic. And so if you're above the mass of the electron and above the mass of the neutrino, which if you're above the mass of the electron you are, then there's no dimensionful parameter in your theory except for temperature and the coupling constant. So that means that n sigma v must go like g Fermi squared t to the fifth. Right? This is the rate. And you can just write that down without doing any thinking at all, right? Because you look at this process, you know this process goes like 1 over mz boson squared. That's effectively g Fermi. That's the amplitude. Therefore, the cross-section has to go like g Fermi squared. That has dimensions of e to the minus 4. You've got to get your dimensions right. You only have one parameter sitting around to help you get your dimensions right. That's temperature. So you instantly know this is the rate, right? It's the only thing that you can write down if you're at temperatures which are above the mass of the electron, but below the mass of the Z boson. So this is the rate. Number density of neutrinos times the cross-section times velocity is g Fermi squared t to the fifth. And so the question you want to ask is, at what temperatures is this in equilibrium? So you're comparing that then to t squared over m Planck. I'm setting the number of degrees of freedom to 1 here. So you can solve this. And you get that the temperature of equilibrium, where this process stops being in equilibrium, is at about 1 MeV. Okay. Since this is going like t to the fifth, I know above that process, above that temperature, this process is in equilibrium. Below that temperature, this process is out of equilibrium. And then there are, of course, two things to note about this. The first thing to note about this is that this kind of estimate is very, very easy. You're just doing some dimension counting, estimating your diagrams, finding out the approximate rates, and comparing them to the Hubble parameter, finding out whether or not they're in equilibrium or not. It takes you all of 30 seconds to do this calculation, right? But the second point of this is that the answer that you get out is 1 MeV. And 1 MeV is, of course, very close to the mass scale in question. So this is actually one of those processes where if you really want to get the numbers right, you better go back and do it carefully. Okay? So this is the exception that proves the rule of what you need to do. Questions about this? So this is the kind of thing that we're going to be coming to again and again, right? You're going to draw some diagram. You want to estimate the rate. You're going to compare it to the Hubble parameter. And then you're going to get some information by doing that. Questions? All right, then I'll say one last thing about equilibrium, just to make this point home, that there are two types of equilibrium, chemical and kinetic. I'm sure, again, this is something that you all remember from your statistical mechanics classes. But if I have chemical equilibrium, that means that I can change the particle number. If I have kinetic equilibrium, then that means the particle number is not being changed, but the temperature is being in equilibrium. Okay? People will often just use the words the particle is in equilibrium And usually it's clear from the context what they mean, but this is something just to always be aware of. If somebody says, assume something is in equilibrium, make sure that you know what kind of equilibrium they're talking about. Good. Great. Now I know that was lightning, 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 but I want to at least have it all down on paper or on chalk. And it's not really the core of what I want to talk about, but it's a set of tools that we're going to need. So now let's move on to the sort of like, that was like the prelude. This is now the lecture proper. So I'd like to move into now this discussion of what it is that we know and what it is we don't know about dark matter. And there's a lot of baggage that comes along with this. Because we really know a lot of negatives about dark matter. We know a lot of things that dark matter isn't. We've done various tests on things and found up to some tantalizing things that we can spend time on, only null results telling us that dark matter is not something. But we don't know at all what dark matter is. Right? And so you should listen very carefully when people like me get up and give talks and say things like, dark matter typically does X, or dark matter usually is like Y, things like this, right? Because we, us, people who've stuck around too long, have built up this huge, calcified knowledge that makes us think certain ways are very natural for dark matter to behave. And that's good in certain contexts, but it also can make us really be very narrow-minded about the possibilities of what dark matter looks like. And I've seen in my own career examples where I've been on both sides of that, where we have presumptions about what's natural for dark matter to do, and then somebody comes along with an interesting model that behaves in a very, very different way. Okay? So if you forget everything that I'm going to say in terms of like the details or the specifics that I'm going to say that dark matter should behave like or not behave like, this is something that you should deeply, deeply remember as you start doing research, if you're doing research on dark matter models, is that you should be very skeptical of people like me telling you that a model is unnatural or kludgy or anything like that. As examples, if you kind of go back in time, right, if you think about the historical evolution, the sort of typical dark matter candidate has changed. So, of course, when we started talking about dark matter, there was no dark matter. Prior to the 30s, nobody needed to talk about dark matter. I'm sure if you went back and you talked to people, they would have told you that they believed, of course, that not all matter was luminous and that there should be forms of matter that were not shining. So that would not have surprised them. In the 70s and 80s, once you started seeing convincing evidence for a separate component of matter, people probably thought mostly that this was gas or brown dwarfs. So that is to say, ordinary matter, but in some phase that behaved differently. Once it became clear that maybe that wasn't such a great example, the favorite candidate for dark matter moved into neutrinos. Right? They were in the standard model. You can give them some mass. That seemed like a nice model for dark matter. But then we've come to understand, from a variety of reasons, both because of the mass limits on the neutrino and because of the cosmological properties of neutrinos, that neutrinos are not dark matter. And then neutralinos became the most popular model. And I think that at this point, neutralinos are probably not the most popular model anymore, but I don't think that they've been replaced by anything just yet. Axions are pretty popular, but I don't think there's been something that's really replace neutralinos as the favored model that most people like to think about. But the thing to point out is just that as time has gone on, our idea of what the most natural dark matter candidate has changed. Each one of these things is very different from the one that came before. If you'd talked to these people about neutralinos, they would have said you were wacko. And if you would talk to neutralinos people about the types of things we're talking about now, they would have also said that you were kind of wacko. So our ideas of dark matter change. What is considered a strange model today may be a natural model tomorrow. I've seen that happen repeatedly. And properties of dark matter that we consider to be unnatural can become natural once we understand broader models. So what about evidence for dark matter? So there's a certain set of things, if you're building dark matter models, that you need to make sure that your model explains. And a very, very, very basic thing is that your model needs to explain dark matter, right? If it is a model of dark matter. So what is the evidence for dark matter? So I'm going to do a very abbreviated history. There's Zwicky and the Coma cluster. So these are galaxies. This is a galaxy cluster. And the observation is that if you look at the motions of a virialized system, then the average velocity of that system can be set by the gravitational potential. So if you measure the velocities of the line of sight velocities of a bunch of these galaxies, then you can get an estimate of what the total mass is if you know how big it is. And what was found is that you needed, this was in the 30s, if you go and you look at this system and you know how much a star weighs because you've seen the sun, and you take the total luminosity of these galaxies and you assume that they're made out of stars like the sun, then you can get an estimate of how much luminous matter there is. And then you can compare that to the amount of gravitating matter from the velocity dispersion. And you find that there's more than an order of magnitude shortage of the amount of matter that you need to explain this motion. But I think that even though we also like to point to this as one of the earliest evidences for dark matter, this is critically not a paradigm shifting thing, because there's no reason to think that there couldn't be some phase of ordinary matter that just is living here, like gas or brown dwarfs or something like that, that's gravitating and we're just not seeing, right? We know there's lots of mass out there that doesn't produce radiation. So the really big change comes with Vera Rubin starting in 1970s and onward, measurement of rotation curves. So the idea here is you take some sort of spiral galaxy. Now I'm drawing it from above, but obviously you want to look at these things from the side where you can actually measure their line of sight motion. And the idea is that you can measure the velocity of these systems as they're rotating. And you can also go way out here and find distant objects that are rotating around with that galaxy to determine how fast the system is moving. And these then give you a measure of the enclosed mass, right? Because you just know the usual story, v squared over r is equal to force. So the circular velocity squared is a measure of the total mass. So this system here tells me how much mass is inside of it. This thing here tells me how much mass is inside of it. So by measuring these as I go out, I see what the distribution of mass is. And what was, of course, critical about this measurement was that not just that it found that there was dark matter, it's that the matter distribution was very, very different. So what was found is that as you looked as a function of radius at the galaxy, so as I move from the inside and go out, I expect that the velocity, the rotational velocity, should go up and then should drop off, right? As I'm moving out to these objects way out here, and I'm moving farther and farther away from the baryonic matter, then if the matter is staying the same and I'm just getting farther and farther away, that velocity should drop. The gravitational force is getting weaker. But that's not what you see. What you see is that the velocity rotation, the circular velocity, is approximately the same as I move out. And that then suggests that there must be a lot of mass out here that I'm not seeing. Right? And this is where things really are starting to be different for dark matter. Because now you're saying that there is a component of matter which is living in a halo. So that's what we refer to out here as the halo around the galaxy that has the dark matter. There's something qualitatively different about this substance that's causing it not to collapse into the interior parts of galaxies like the stars are. Right? So stars and gas have cooled, settled into the center of this system, but this other material has stayed out. Now that doesn't mean that it's exotic, it doesn't mean it's non-baryonic, but it means that this stuff behaves qualitatively different from ordinary matter that we've seen. The next piece of evidence, and this is now very commonly used, is lensing. And this can come in the form of weak lensing, where you're just learning about the material, the matter distribution in aggregate, or in strong lensing, where you look at very dramatic lens systems. So the idea here, right, is that you've got some object, like a galaxy cluster. You have an observer, which is you. And then over here, you've got some galaxy. And the image of that galaxy gets distorted by the mass in between you and it. This can then have two effects. One is that you can look at this object and you can see it stretched in a particular way. That gives you information about this object here. Or you can look, and if I have many, many objects, then as they get lensed, their properties get elongated and stretched along certain axes preferentially, and you can determine the amount of mass between you and the systems statistically. Okay. And this here also points to evidence for dark matter. That is to say that the amount of lensing that you observe in these galaxy clusters is much larger than what you could explain from the ordinary matter alone. Yes?
So all of these methods depend on you knowing how much the visible stuff is, right? Like what the mass of the visible stuff is. How do you measure that?
So some of these things depend on that. This one, for instance, doesn't really depend on that. This is really about a distribution here. Similarly, there are examples of this where it's more about distribution, where you can see the lensing as you move out from an object, that it tells you that there's matter where you don't see objects. But if you look at the stellar population, we have a pretty good understanding at this point in our lives of how the colors of the stars and how old the system is combined together can give us a good estimate of how massive those objects should be. So, yeah. I mean, given that the amount of dark matter is off by a factor of 6 from ordinary matter, it's not in the noise from those sorts of things. But wait 1 second, because there's one more that is critical that also does not depend on knowing anything about stars. And that is power spectrum of perturbations. So you go out and you measure the CMB. Here's my poor version of the CMB. But you can also go out and measure something like the average overdensity in a volume of space and look at that as well. And I'll say what these things are that I wrote in a second. This is a very, very, very important test of dark matter. Okay? So as we discussed earlier today, and as you learned about last week, the universe starts with these tiny inhomogeneities, 10 to the minus 5. Dark matter in the early universe can have those perturbations grow very slowly until matter domination occurs, and then they start growing very rapidly. And by looking at the presence of those perturbations, we also get information that there is dark matter there. Why do we get that? Well, the critical difference, and I'm sure that I'm being redundant with what was said last week, but I'm going to say it for completeness, is that if you want to talk about, say, the presence of ordinary matter versus the presence of dark matter, they show up in this very, very differently. Because baryons are tightly coupled to electrons, right? So I've got protons floating around. They tend to flow with electrons because the electric charge is going to make it so they don't have net charges present in the universe. The electrons are light and have charge 1, so they tightly interact with the photon bath. Okay? Now the photon bath has pressure. So if you've got baryons and electrons, which are tightly coupled to the photon bath, then the evolution of their perturbations is very different from that of dark matter. Right? What do I mean? I take a bunch of protons and I try and squeeze them into an overdensity in the early universe when there's a lot of photons around. They feel the pressure of that overdensity and it pushes back. Okay? So if I wanted to just start growing a delta rho over rho and just letting it adiabatically grow, that's not going to happen with baryons because of the pressure. In contrast, dark matter, even in the early universe, even when it's a slower logarithmic growth, that overdensity can grow. Okay? So remember, we had this difference in time periods, which is that you have matter radiation equality at around an EV, and you have recombination at around 0.3 EV. So even at a very, very, very gross level, perturbations in dark matter are growing proportional to A in this intervening period, whereas perturbations in baryons cannot grow until after recombination occurs. Once recombination occurs, then protons and electrons have bound together into neutral hydrogen, and they're no longer tightly coupled to the photon bath anymore. Okay? And after that, after this temperature, ordinary matter will start just acting like, or baryonic matter will start acting like ordinary non-relativistic pressureless matter, but before that it's not. And that means that you have this huge history of the universe when baryons have been feeling the pressure of the universe and dark matter has not. And that imprints itself in looking at the CMB and looking at these average perturbations that you see in the universe. So you can go back and you can just test. You can just look at the universe and you can calculate how large should I see the average overdensities be compared to how large those average overdensities are. And I can look at that at a given scale. Okay? And the reason that I look at it at a given scale is that the very, very largest scales have only started interacting with themselves late in the universe, whereas the smaller scales, because of the smaller sound horizon, had the opportunity to interact and test the properties of particle physics earlier on. So these parts of the universe here are sensitive to higher temperatures, and these parts here are sensitive to low temperatures. Okay? And so in this way, these measurements of the CMB and of structure give us information on the properties of dark matter, not just after recombination or after an EV, but really going back to very, very early times. And indeed, the smallest scales that we can look at with any sort of reliability are the Lyman alpha forest. The Lyman alpha forest tells us about structures that go back to, that tell us about the properties of dark matter back to times of temperatures of about a keV or so. So the lesson from all of this is that dark matter has been evolving as a pressureless cold fluid from temperatures of about a keV and below. So the upshot of this is that dark matter, cold dark matter, has basically been cold dark matter from temperatures of about a keV and later. At 10 keV, I can't tell you. At 10 keV, maybe it was some exotic fluid. At 10 keV, maybe it was moving relativistically and then stopped suddenly, if you come up with a theory that does that. But after a keV or so, this stuff was non-relativistic, cold, collisionless matter to a very good approximation because it explains these data so well. And the last piece of evidence that I want to throw in is not really evidence for dark matter per se, but it's something that's, I think, worth keeping in mind, and that is Big Bang nucleosynthesis. So you know now that the abundances of light elements like helium, deuterium, and lithium all together can be explained by a baryon to photon ratio of 6 times 10 to the minus 9. So, right, you go out, you know how the universe is. It's a pretty simple system. You've got neutrinos, you've got matter. You run the clock backwards, and you calculate the freeze out of neutrinos. You calculate the combination of all the elements. And you find that you can explain everything as long as the baryon to photon ratio is 6 times 10 to the minus 9. Which then you count photons, and then you multiply, you move this number of photons over there, and that tells you that omega baryon, which is the energy density in baryons divided by the total energy density in the universe, of 0.04. So what does this tell us? If you believe that there is dark matter out there, that is, that there is some energy density which is not explained, that is necessary for the evolution of structure, that is necessary for explaining the Hubble constant. This tells you that if you think that the omega matter is around 0.3, then that's telling you that there's a big deficit, even back at temperatures of an MeV. Of course, this doesn't tell me that I actually needed dark matter back at that time. It simply tells me that at that time, this stuff, the amount of baryons that I had back then are not enough to give me dark matter now. And that's important because, for instance, if you wanted to have something like some exotic property that would cause those baryons to then form into exotic matter or tiny black holes or something like that between that time and keV, that's probably not possible because the amount of baryons back then was pretty small. So this is all the positive evidence, and this is, of course, not exactly positive evidence, but this is all sort of the positive evidence that we have for the existence of dark matter. Why do we want to put it all on the board at the same time? The reason why we put it all on the board at the same time is because these are qualitatively very, very different types of observations, right? You have things that are sensitive to the properties of the universe at temperatures of an EV. You have things that are sensitive to the properties of the universe at keV. You've got systems that are related to just knowing about the gravitational properties of matter. You've got systems that about the rotation curves that are just questions about how stars are distributed in the late universe. Early universe, middle universe, late universe, small systems, big systems, very big systems. These are just tests that are going over on a variety of times and a variety of scales, And they're all consistent with this idea that there's a component of energy density of the universe which is collisionless, cold, and is about omega of about a quarter, okay, today. And that means that you can't simply come out with a theory that says, I'm going to explain rotation curves and say that you've explained dark matter, right? There's a lot of data that's pointing to dark matter. And the important thing is that at this point in history, the conventional, the boring explanation is that there is dark matter, okay? I think I want to make that very, very clear, that this is not, this is not like reaching out. This is now a very well-tested theory that makes a lot of predictions, and those predictions at a very, very good level have been borne out. This idea of cold collisionless dark matter. Doesn't mean it's right, but it means right now that that is the leading conventional explanation. Somebody's going to ask about MOND, right? Modified gravity. My attitude about MOND is that it is a very, very interesting subject, right? But that's not where the data are pointing, okay? So if you want to work on MOND, there are 3 features that need to be true about you. You need to be very smart, because it is very hard to come up with a good MOND model. You need to be intellectually honest with yourself and with other people, because that's just very important in general. And third, you should have tenure, because you may not get it working on MOND. And we'll discuss some MOND-like theories later. Questions about any of this?
With this temperature around KV scale, could you already exclude some theories like axions, like not axions, or could you recommend?
So that's a very, very good question. So axions, right, have typically masses which are more like micro EV. So the critical thing is that at T of KeV, the dark matter better be acting like a cold pressureless fluid. Now, if it's in thermal equilibrium, kinetic equilibrium, then that would absolutely be true, that you couldn't have that. So if I had a micro EV particle that was in thermal equilibrium, then that would not work. Now, axions, because their coupling constants are so weak, because they're suppressed by like 10 to the 12 or what have you, typically, they are not in thermal contact with us at this late time. And so you end up with a cold fluid that was formed much earlier, and it stays cold. So even though this is a very, very light particle, it is, in fact, acting like a pressureless cold fluid at that time. That's actually a very, very good point, because this idea that we need dark matter to be acting like this at temperatures below KeV doesn't necessarily mean the mass has to be above a KeV. It just means that at that temperature, this is how it's acting. Questions? So, what do we know about dark matter? That was evidence. So now we're getting a bit more into the model building aspects. So you're going to start building a model. What do you not want to spoil? So at the 0th order, this is massive. So that is, it has an equation of state approximately equal to 0 since KeV. And there's no signs of DAO, dark acoustic oscillations, right? So we see baryon acoustic oscillations in the distribution of matter in the universe, which is evidence of the fact that the baryons were pushing off themselves. At this point, we do not see any signs of dark acoustic oscillations. So you want to make sure that your theory does not predict that there are any that should show up. The theory must be neutral. Now, how neutral? There's an old but good paper by Dubovsky, Gorbanov, and Rubtsov, where they kind of test this, right? Because dark matter has to be neutral That's what we mean by dark, right? But how dark does it actually have to be? Well, if you gave dark matter a millicharge, then depending on the mass of the dark matter and depending on how large that millicharge was, eventually this thing would come into tight coupling with the photon bath, and then it would have the same sorts of properties as baryons, right? You'd essentially see dark acoustic oscillations, but they wouldn't be because of dark matter interactions, they'd be because the dark matter had charges. And so basically what you want to require is that dark matter should not be tightly coupled to the photon bath, which is what these people actually then probed. And so you can kind of work it out that this is sort of an approximate relationship. But so for a charge of 10 to the minus 6 and a mass of 10 to the 10 eV, this is tightly coupled. And for a charge of 10 to the minus 5 and a mass of 10 to the 14 eV, this is tightly coupled. And there's sort of a line that does that on the charge mass plane. So everything on this side of that, if you've got a charge which is larger than that, or you have a mass which is lighter than that, then you'll be tightly coupled to the photon bath, and that will be excluded. Okay? For details, I would point you to this. But the point is really just that even if dark matter has a very, very, very small charge, even a tiny millicharge, for particles that we often talk about, that would be enough to make it tightly coupled to the photon bath, and that would exclude it. We know that if it talks to the Z boson, then it could appear in the decay of the Z boson. And the invisible width of the Z boson has been measured very well. And it's consistent with a Z boson decaying into 3 neutrinos. So the Z boson decays mostly visibly, but obviously has its decay into neutrinos, and the invisible width of the Z is entirely accounted for by those neutrinos. So if dark matter talks to the Z boson and it is light enough that it can appear in the decay, then the coupling should be something like 10 to the minus 1 times the neutrino coupling, which is not a huge constraint. As an example of random things that one should worry about, just one example. I want to give you an example of a model that has constraints on it that are just sort of out of left field, but are the kinds of things that as you start building models you'll encounter. Let's suppose that you wanted to imagine that dark matter was made out of a composite object like ordinary matter, right? Ordinary matter is made out of a proton and an electron, plus 1, minus 1. They bind together, they form a neutral object. Maybe you want to have a theory where instead there's a very, very heavy particle that then also binds with something else and forms some sort of dark atom. Also electrically charged, but much, much more massive. And so those things are much more tightly bound together. So they bind together much earlier in the universe. And when they bind together earlier in the universe, then that means that you don't have problems with the CMB and things like that because they were neutral early on. That's a reasonable model. But it turns out that if that were the case, those heavy particles, those heavy plus 1 charged particles, would also form bound states with electrons, and you'd end up with hydrogen. Well, a form of hydrogen, be very, very heavy hydrogen, right? So you'd have the proton would be replaced by something which could have a mass which was like a TeV, for instance. And then that is something you can look for because it will form into water, right? Because chemically this will act just like hydrogen. So it'll bind with another hydrogen and an oxygen. And that will then be present in the oceans. And you can go and you can sift through the oceans and you can pull this stuff out and you can look to see whether there's any of this stuff there. And you would have heard about it if there were. And the abundances, so that is the fraction, abundance, of this. The fraction of ordinary water, which is in the form of heavy water, is less than 4 times 10 to the minus 14 for dark matter in this mass range. Okay. And I point that out not as because I think this is the best model or this is the next model you're going to think of or anything like that, but just to illustrate the fact that when you start going down, these things are all pretty generic, right? But once you start going down the path of your specific model, you really need to think carefully about what what's left over. What's left over from the early universe, what's around today, how do you test it? Think hard, because experimentalists are out looking for all sorts of crazy stuff, and it might have looked for your model as well. Let me move on from that, though. OK, so dark matter has to be dark. This is how dark it has to be. That's how dark it has to be. It can't couple to the Z very strongly if it's lighter than it. It has to have a charge, a millicharge, which is less than about 10 to the minus 5 or 10 to the minus 6, depending on mass. And you can't build it out of composite charge things, at least as I've described them. There are other models of composite charge things that are fine. So that's dark. Next is cold. Now, cold versus hot is actually a somewhat ambiguous statement, because all dark matter is cold today. Even when you talk about hot dark matter, it's cold today. Okay? Hot dark matter are like neutrinos, right? So people talk about an EV or a few EV neutrino. But the temperature of the universe today is like 10 to the minus 4 EV. So those neutrinos have been non-relativistic since Z of 10,000 or something like that, right? So even that hot dark matter has been cold for a long time. And of course it has to be, because you can't form galaxies out of stuff which is moving at the speed of light, right? Stuff that's moving at the speed of light will just stream out of it. So when you talk about cold matter, it's a little ambiguous what you mean. You might mean the stuff was cold at formation. You might mean that it became cold early on. But what it really effectively means is that this stuff has been cold, so that is non-relativistic, since temperatures of a KeV and below. And the contrast for that, which was hot, you can imagine you start with some overdensity of hot dark matter. And if you have some overdensity of hot dark matter, then over the history of the universe, that overdensity will smooth itself out, right? You can imagine I have delta rho over rho. I put a lot of stuff right here. But if it's moving relativistically, that stuff is going to spread out and eliminate that initial perturbation. So the fact that we see small objects like dwarf galaxies tells us, and the Lyman alpha forest tells us, that dark matter couldn't have been hot at temperatures of a KeV. And then matter which was approximately relativistic at a KeV we call warm. So cold doesn't have a clear meaning, but what it really means experimentally is that this stuff had to be cold after a TeV. You can quantify this a bit better. And you can ask the question, if you want to be very, very, very particular about this, there's a paper by Carr, Das, and Sethi, where they kind of look at structures and they ask, let's suppose that we have dark matter that started as a just background energy density that suddenly at some redshift converts into dark matter. Okay, so it's basically cosmological constant, and then boom, it transitions to dark matter. And they find that you have to have that transition happen, has to happen before about 200 eV, which is basically this KeV number. So it's got to be dark, it's got to be cold, and it has to be collisionless, that is to say pressureless. So dark matter is non-interacting. Now, what do you mean by that? What you really mean is that if you take lambda CDM and you run it assuming that dark matter has no collisions, you get a description of the universe which looks very, very close to what we observe. Okay? So if you start adding things to that, then all that can basically happen is things can go bad. That's kind of the approximate when we say it's non-interacting. Okay? Now, in some specific cases, there are very specific things that can go wrong when you add interactions. Yeah?
How much dark matter can be not cold, say hot? And if you have some proportion that is hot, does that change the transition temperature?
So this assumes that all the dark matter transitions, probably the best way to quantify that statement is the current cosmological bound on the sum of the neutrino masses, right, which is around 0.7 eV, depending on who you trust and which data sets you want to combine, but it's in that order. It depends a little bit. So when you look at this plot, which is a measure of, this is the scale factor here. So these are small scales, and these are large scales. So this is some inverse distance, right? This is the wave number k. What you're looking for when you're talking about adding a component of hot dark matter to your model, there's two things that you can see. One is that at some temperature here, right? So remember, like we said, all dark matter is cold today. Right? So that means that there was some temperature at which time that stuff became cold. Right? That temperature corresponds to a particular time in the universe when the size of the universe was whatever. Right? So on scales shorter than that, the universe has been smoothed out. And on scales larger than that, the universe never knew that this stuff was hot. Right? So if I, for instance, have stuff which was moving rapidly and could stream out to a certain distance, then stopped, maybe below 1 megaparsec, it's completely smoothed itself out. But at the gigaparsec scale, it hasn't had an opportunity to smooth that out, right? Because it became cold. So there's two features you're looking for. One is that there's some particular scale factor where you see a transition in the shape of this, right? So you would see some break here. So this is nice, acting like cold dark matter, and then here you'd see some break. And then this spread between what you predict and where this stuff is the second thing that you can look for. So there's both this location and this spread here that are relevant for placing this constraint. So you can't totally just ask the question about how much you have, because how much hot dark matter you have relates to how big this split is, but the temperature at which the stuff became non-relativistic relates to exactly where the break occurs. And it's a combination of those two effects that you actually can place constraints on, right? And in sort of the limiting case, if I had half the dark matter, which was hot, but then became non-relativistic at a temperature of a keV, there's no constraints, right? Because then that's basically off the plot, right? Then this looks like cold dark matter, and then you have a big abrupt transition somewhere here that you just can't see, right? But anyway, so the very short answer to your question is, how much dark matter can be hot? Well, probably the easiest way to quantify that is in the context of the limits on how much what the mass limit on neutrinos is from cosmology. But the longer answer to your question is that you really need to tell me not just how much there is, but also the temperature at which it went non-relativistic. Which, if it's not in equilibrium with the standard model, or if it decoupled from the standard model at a very early time, could be different. But it's a very, very good question. Right. So, dark matter is not interacting. There are specific things that can go wrong if dark matter is interacting. Right? If you imagine a galaxy, in the core of the galaxy, you have all these slowly moving particles that are kind of sitting there in the center of that gravitational potential. And you have these particles coming in at a very high velocity from the outer parts of the galaxy that come in at escape velocity. They come in, and if there's an interaction, they can smack into the particles in the center and transfer energy from these high velocity particles to these cold particles. So now you have a transfer which is going to take these cold particles and gradually flatten them out, right? So they're going to push out the center and flatten out that. And that could be good if you only do a little bit. But if you transfer too much energy in your system, then you can actually end up with particles that have velocities that are above the escape velocity of the system. And if you have particles that have energy above the escape velocity of the system, then the system can start radiating those particles. So gravity would start emitting dark matter particles from it, cool itself off, and it would condense. And that's called the gravithermal collapse, which is essentially sort of it's not exactly, but the same kind of idea of what happens with ordinary matter, where it has a radiation process and allows it to cool and condense into the center. And we know dark matter doesn't do that. So at a leading order, you just ask the question, has dark matter interacted in the history of the universe? And if it has, then you should be worried that that might screw something up. And if it hasn't, then you're fine. So you start with this question, n sigma v times tau. You set that equal to 1, where n is the characteristic number density of whatever system you're talking about. Sigma is the cross-section, right, that you're interested in studying. V is how fast, the characteristic velocity of your system. And tau is how long your system's been around, which is usually about the age of the universe. And what's funny is that you can plug this into a lot of different systems, and you'll end up with comparable answers. And the answer that you get is something like that the cross-section for a TeV mass particle should be less than about 10 to the minus 24 centimeters squared. The bullet cluster, the very, very famous cluster, or two clusters, where they came together and the ordinary matter collided and slowed down, and the dark matter passed through itself and continued on moving, gives you a limit which is .47 centimeters squared per gram, which is the language that your astronomer friends will like to talk in, which is basically the same as this limit. The way I like to phrase this, these limits, is that sigma over m should be less than about 100 MeV to the minus 3. That's, I feel like, a very nice round number that you can put in there and remember. Two caveats about this. Okay? The first caveat about this is that almost all the limits that you'll find in the literature are operating under the assumption that this cross-section here is velocity independent. It's just some number. So you're assuming that you've got some big rock, and there's some other rock, and they're colliding with each other. And that's a perfectly reasonable model of a cross-section if you're colliding rocks, which dark matter could be a tiny, tiny little rock, right? But if you think about, for instance, how electrons interact, that is absolutely not the case, right? Electron cross-sections, as they scatter off each other, are very, very velocity dependent, right? And that's because they're exchanging a very massless, a massless mediator, the photon, right? So that means that your cross-section has a q-squared dependence in it, and that q-squared translates into a velocity dependence. So there's sort of approximately two classes of models, very, very roughly speaking. There's the ones that have approximately constant cross-sections, in which case you can really compare all these different systems. And then there are ones where you have some sort of long-distance mediator, and the ones with long-distance mediators often will have cross-sections that can be wildly different at different scales, right? Because if you're talking about the systems that this is testing, they go from dwarf galaxies, where you're talking about approximately 10 kilometers per second, up to galaxy clusters, where you're talking about 1,000 kilometers per second. So if you've got any sort of velocity dependence, you're talking about orders of magnitude changes in the overall size of the cross-section between those systems. So that's the first point to remember when you're talking about self-interacting dark matter and limits. The second thing to remember about self-interacting dark matter and limits is that there's an unfortunate accident of nomenclature, which is SIDM. SIDM stands for self-interacting dark matter, right? This is dark matter. This is what Spergel and Steinhardt originally talked about, dark matter that interacts with itself in a way that changes its properties. However, this cross-section, if you're in this mass range, this is approximately the same size of a cross-section that you'd get if you had something that was exchanging pions, right? And nuclei exchange pions, and we call those strong interactions, right? So if I collided two, heavy nuclei with each other, they could have cross-sections that are also characteristically around this scale. And you would call that strongly interacting dark matter. And that would also be SIDM. And so it turns out that SIDM, self-interacting dark matter, that has cross-sections which are of the order that you want them to be relevant for the cosmology, have cross-sections which are comparable to SIDM, strongly interacting dark matter models. But they are not the same thing, okay? And these things can get conflated in the same way that neutralino and WIMP often gets conflated. Oftentimes you'll see SIDM be sort of indistinguishably thrown around as both strongly interacting and self-interacting dark matter. Questions? Okay. So we're still talking about the interactions. There are long-range interactions. So you can imagine that dark matter doesn't just interact via gravity at very, very long distances. Perhaps dark matter has some sort of Yukawa interaction that only dark matter feels. And if that's true, the gravitational potential that dark matter is experiencing would be different from those of baryons. And what would be the upshot? Well, you have the equivalence principle operating in galaxies. If I have a dwarf galaxy orbiting around an ordinary galaxy, if that dwarf galaxy, the dark matter inside of it, felt a stronger gravitational pull, then it would rotate around slightly faster than the baryons inside of it would want to rotate, right? Everything is being pulled by the center of the galaxy, but the dark matter is being pulled a little bit more. It'll rotate a little bit faster. The baryons will lag, and you'll end up with a tidal stream lagging behind your dwarf galaxy. So here's your central galaxy. Here's your dwarf galaxy. And if this is the velocity of the dark matter, and then you've got baryons inside that are being pulled with a different speed, then eventually, as the dark matter orbits, the baryons will leave some sort of tidal stream behind it, okay, which is not observed. And so Kesden and Kamienkowski quantified this, where they said that they parameterized it with some number they called B, that should be less than 0.2, and this is the strength of the interaction compared to gravity, okay? So this is now some people have qualms with this particular analysis, but I think those qualms are sort of at the detail level. If you have interactions which are comparable to gravitational strength for dark matter that distinguish dark matter's gravitational potential versus baryons' gravitational potential, that would be strongly ruled out by these sorts of systems. Okay, so dark matter has to be cold, collisionless, non-interacting. Well, that's collisionless. What do I do with the eraser? So there's one more property that it has to be, and that is stable. It has to be here. Now, Tracy will talk about specific decay modes. So if dark matter decays into electrons or muons or photons, then there are all sorts of incredibly stringent constraints on those. But at a very basic level, you could say, well, what if dark matter is just decaying into some invisible radiation? Hidden neutrinos or hidden photons or something like that. And so there's a fairly recent paper where they come up with this constraint. That the fraction of the universe which is in the form of decaying dark matter. So you imagine that dark matter has some part of it which is decaying. Maybe that's all of it, maybe it's just some fraction of it. And that stuff is decaying at some rate, and that rate is just some decay to some invisible stuff. The impact this has is that means that the energy density in dark matter is not redshifting like a to the minus 3 anymore. It's redshifting like something which is something between a to the minus 3 and a to the minus 4. Because some of that energy density is going from dark matter into dark radiation, and then that dark radiation is redshifting a little bit faster. So this kind of a fluid would have a different equation of state, a different effective equation of state parameter, and that's what they quantify. And so it's actually a surprisingly strong constraint, if you want to think about it, which is that if you have, put it in this way, if all the dark matter is in the form of a decaying stuff that's decaying to radiation, the lifetime of that stuff better be longer than 10 times the age of the universe. So it's not just enough that that stuff be stable today, that stuff has to be stable for a long time. Okay? And then you can play the games of the different fractions. So these are sort of the generic constraints on what you want your dark matter to be like. So the last thing then that I want to say today is to start this transition to scales of dark matter. Because what we're ultimately going to want to do is we're going to want to start talking about specific models, specific particle physics models, and what they're for, what they're good for, what they're not good for. So the thing that we want to then have in the back of our mind are the energy scales. So in principle, the particle physics scales that you can play with are 10 to the minus 33 eV and 10 to the 19th GeV, 10 to the 28 eV. So you have 60 orders of magnitude that you're starting with of mass range where dark matter in principle could be. Right? A priori, there's nothing wrong with any of those. But there are some problems. If you have a boson, then, and this is not going to be well to scale at all, then below 10 to the minus 22 eV is excluded for a boson. And the reason for that is that 10 to the minus 33 eV is the current Hubble parameter translated into natural units. So that's effectively the size of the universe. Okay? So if I have particles that are lighter than that, then they're lighter than the size of the universe. They're effectively massless. There's nothing that you could do. There's no test you could have done in the history of the universe to tell you that they were massive versus massless. Right? It's experimentally impossible to know within the uncertainty principle of the universe. But at 10 to the minus 22 eV, you look around yourself and you see dwarf galaxies that are fairly small. And if the dark matter had a mass that was smaller than that, the de Broglie wavelength of dark matter would be too long, and you would not be able to confine the dark matter inside those halos. So just the fact that you've been able to squeeze it into the small halos that we see tells us that the mass must be at least 10 to the minus 22 eV. And dark matter that's right on this transition is known as fuzzy dark matter. There's an equivalent bound for fermions, which is around 100 eV. This is known as the Tremaine gun bound. And it's a similar idea. You take a galaxy, except for instead of putting bosons in it, now you're putting fermions in it. So you start filling out your distribution, your Fermi-Dirac distribution, you're stacking up fermions, and eventually you get to a point where the velocity of those fermions is too high that they actually are going to escape the object in question, right? So if I had fermions that were lighter than around 100 eV, then the dwarf galaxies that I see would actually not be capable of containing the fermions inside of them in the sizes that we observe. Okay? So essentially you'd start putting in the fermions that you needed. By the time you get to them, they're at velocities which are too high and they're escaping out of that system. Now, up here, you have, so that's sort of what you are bound from below. Up here, you have WIMPs, which I'll loosely put at sort of 10 GeV to 1 TeV, which is singled out as an interesting scale. And then you have a few other scales of note here. KeV if they're in thermal equilibrium, MEV for Big Bang nucleosynthesis. But by and large, anything up here is OK for dark matter. Okay? So you're playing with a huge range of scales. And one of the things that's very, very exciting in the last decade, I'd say, is that previously we've been spending a huge amount of energy living in this window and thinking about this window. And it's a great window. I'm not saying it's not a great window. It's a great window. But there's all this other space that has not been nearly as well explored. And so hopefully what we'll talk about then this week are some of the explorations both in here as well as out here. So I'll stop there and we'll pick up tomorrow.